Earth science time.
Welcome back, fam.
Earth science time.
Is this what you are?
I about wrote Earth science time too. We're going to call this one, please. We're going to call this one causes and effects, oh that's nice, of plate tectonics. Let's begin this. Shouldn't put a period at the end of a title. This is not very, it's not going to seem like really good handwriting. These markers were stored in my desk upside down. All the ink is run to the bottom. So eventually it'll get better the further I go. I mean, the handwriting itself won't, but it'll be more legible because the marker will get better. Firstly, even in Alfred Wegener's time, who we talked about last time, even in his time, there were two fundamental flaws he had with his hypothesis. We now know, as we said in the last one, that his hypothesis was true. All geologists accept it today. That's probably not true, but reasonable geologists accept it today. But there were two problems that even he couldn't think of the answer for. And the first was that what is causing this, right? That's a really basic question. Like if you claim, Alfie, that the continents are moving apart, what force is causing that, right? People have understood physics, intuitively, in your instincts, for all of human history, but people have understood physics on a mathematical level for 500 years. And so he was saying the plates are moving. And so every reasonable person was asking, what is causing, what force is driving the plates, right? He couldn't answer that. He thought, in fact, he posited that maybe it was because the Earth is spinning and that it's causing the plates to spread out, which we now know is false. But even at the time, they were able to mathematically prove that that was wrong. The Earth was not spinning fast enough to cause that much force on the plates. So he didn't have an answer for that. Sorry, I'm gonna.
But the Earth is spinning. Right?
The Earth is spinning. That's correct, but it's not what causes the plates to move. And the second reason is that all of his evidence, which he had even by the time before he died, all of his evidence was for the movement of the continents, and no one really knew anything at all about the bottom of the seafloor. And so, in his idea, really in his hypothesis, the continents were just kind of bulldozing through the seafloor, and everyone's like, why doesn't the ocean get smaller? Why doesn't the ocean curl up on the edges? Or if it's moving through the seafloor, is the ocean just caving away underneath? And he couldn't answer that either. And so we're going to talk about the answers to those two questions. So firstly, because we talked about it before in 8th grade, what force does drive the movement of the continents, or the movement of the plates?
Rising magma?
Yeah, okay, so the rising up of magma, we had used a different word for that, but yeah, magma rising up and then moving, which carries the plates along with it. But first let's draw this little, here I've got, this is really a good drawing. Can you tell what it's supposed to be?
Pretty good circle. Yeah.
It's a pretty good circle,
Is
but
it Jupiter?
it ain't Jupiter. It's supposed to be planet Earth. Planet Earth, to address the second problem with Wegener's hypothesis first, why isn't it a problem that the continents why isn't it that the continents are just bulldozing through the ocean floor? Why is that not the case? Why is that not actually a problem with the hypothesis?
Say that again.
Because what's moving?
The plates.
Yes, but remember in his, it's just the continents moving, and they're kind of plowing through the
So
ocean.
he doesn't know about the plates?
Exactly. Okay, so that's it. Is that the oceanic crust is also made of plates, and so that's the answer. The very simple answer to his second problem is that every part of planet Earth is on some tectonic plate, even the oceans, right? So all of planet Earth, we're going to write this as our first tenet of plate tectonic theory, which is different from continental drift. Remember, I told you to keep those separate in your mind. But the idea of plate tectonics, the theory, we say, of plate tectonics, the first supposition of it is that the whole Earth, the whole Earth, that's what I said, but is that what I meant? What part of Earth?
Surface.
Yeah, the surface. What did we talked last time? Not just the crust, we call it the lithosphere. Earth's lithosphere is broken up into interlocking plates. You might have already guessed, but this is not a perfect representation of the way that plates look. There is a pretty good one on page 480 in your book. You can look one up online also, but we're just looking at this picture of how the plates fit together. And not only that, but this little picture here on page 480, and probably one you can find online, has what else is interesting about this besides just that we can see where the plates are.
Yeah, label.
Where they're moving.
Yeah, we can see the direction they're moving, the general direction of their motion.
Yeah.
And so we can see from that I tried to draw this, oh, I made a big mistake. This should be what? There's not an Atlantic plate, is there? This is made of the North American plate and the Eurasian plate come together in the middle. I should have known that, I'm sorry. And they're moving how?
Away.
Yeah, away from one another. This is still not a very good drawing, but they're moving away from each other. So what could we say is the second supposition? The first one being the Earth's lithosphere is broken up into interlocking plates. What could the second supposition be? What are they doing?
I'm moving.
Yeah. The plates move relative to one another. We're going to talk about the three ways that these plates can move. And we're going to talk a little bit more in depth about a couple of them also. So in general, if we have two things like hanging out pancakes or waffles or dinner plates or tectonic plates, how can they move relative to one another?
Away or together?
Yeah, okay, so let's talk about, we have two to start out with. Away from one another
Yep.
and towards one another, squished together. And then there's a third.
Underneath.
Yeah.
That counts as together, right? Because if you take it
They
underneath,
can
they're both
uplift. Like,
still together.
What? I don't know.
They don't move at all. They just,
They just-
Look at,
Yeah.
look with me at
Yes.
the relationship between, for instance, the Cocos plate. Do you see that down in the southwest of Central America, and the motion of the Caribbean plate. So you can kind of tell which direction those things are moving. At the interface between those two things,
oh, so they're moving like this?
they're moving not
They're
not
sliding
together.
past
There you
each
go.
other?
They're sliding past each other.
Oh.
So they can move in three ways. We call them transform boundary, which is the one we just talked about.
just slide past each other.
Yeah, and we're going to draw these. I'm going to try to draw them in 3 dimensions. You can draw them in 2 dimensions if you like. It would be easier, but I like to make things difficult for myself. So in a transform boundary, they're sliding past one another. Right? We do the hand motions with this in 8th grade. You know, they go like, you can hear my dry hands rasping together because there is friction between these, and that's what causes what might happen at this kind of plate boundary quite frequently.
Heat.
Yes, definitely, but also if they're sliding past each other and they suddenly move, earthquakes. This is the most common kind of plate boundary to cause earthquakes. So a transform boundary is where they slide past each other. This can occur as our Cocos plate and Caribbean plate. This can occur with an oceanic plate, Oceanic Continental, doesn't matter. Any two plates that are rubbing past each other in this way is called transform. Another way they can move is what we call convergent. And this one they're doing what probably?
Moving together?
Yep, moving towards one another. Oh, this is getting worse and worse the further down I go. They're moving towards one another. We're going to talk about 3 special cases of this, which is also in a really nice diagram on page 483 if you want to turn to 483. But I'm also going to draw them on the board much worse.
483.
Yeah, so within our, so we have the theory of plate tectonics. We've separated that into how they move is going to be A and B. So I'm going to have I, B, and we're going to have I. There we go. This is like a little outline. Depending on the types of plates, these things behave differently. And so, what are the 2 types of plates?
Oceanic.
Oceanic, which is made of what rock? Generally, basalt, and continental, made of
Granite.
granite. And we talked already, which of those things is more dense than the other? Basalt is the more dense. So what happens is, let's start with, I think your book starts with, oceanic. I'm not going to really have room to describe these, but hopefully you can just remember them. When these two things, they're both quite dense, and so when they squish together, whichever one is more dense, or maybe whichever one is moving differently, is going to subduct beneath the other. So there will be subduction here.
So whichever one is more dense?
Yeah, one of the oceanic plates will subduct beneath the other.
The more denser one goes underneath.
Yep. And that's not the only thing that matters. If there is one that's more dense, that one will go underneath. But there's also, it relates to their motion and what they have on top of them, you know. The next one is Oceanic Continental, and in this case it's, the Oceanic is always going oh, I put the wrong vowel there. Continental. The Oceanic will always be more dense, and so also subduction will occur here.
Continental will go underneath.
The Oceanic will go underneath because the Oceanic is always more dense. But what's interesting about that is that, I'm going to do a little hand gesture, so draw your attention up to my hands. Look at the hands. When the Oceanic plate goes under, when it gets pushed down to here, what's going to happen to it?
Isn't it gonna?
Yeah, it melts. It melts, and it does that partially because it's hot down here, but also partially because it's dragging water down with it, and the water turns to steam because it's very, very hot. And that causes magma to build up down here, and that flows to the surface. And so when we have a continental plate and an oceanic plate, and the oceanic plate's going beneath, there's going to be a volcanic mountain range formed, but it's going to be several miles inland, right? So that's why we see things like the Cascade Mountains, the Andes Mountains, Mount Fuji, God bless you. There's all these volcanic mountain ranges on the edge of oceans because the continental plate is subducting the oceanic plate beneath it. And then the third type we have continental, I can't ever spell it right, continental, I did it this time. And this one, they're going to do what? We call it, do you remember from 8th grade, we called it?
Why?
Convergent.
Yeah, they converge, all these are convergence, but they uplift. They uplift into a mountain range. We sometimes call it a crumple zone. Crumple zone. And then before we go, because the bell's going to ring here pretty quick, we have divergent boundary. What's going to happen in that one? Boundary.
Go away.
Yeah, they're going to move away from one another. Oh, golly, this is going to be the best 3D drawing you have ever seen. Ugh. In a divergent, they move away from one another. And this happens in two places. Mid-ocean ridge, which we talked about in the last video, as the plates move away from one another, and at a rift zone. If it's continental,
Wait, what's that first one say?
mid-ocean ridge, which is oceanic plates, and a rift zone can happen in continental plates. There are two rift zones that I'm aware of and that I talk about quite a lot. The East African rift zone, where all of Eastern Africa is rifting away from the rest of Africa, and the New Madrid Fault in Missouri in the United States, which is going to eventually become its own little continent, so that will be nice. Before we go, I said one last thing, but before we go, what's causing all this? What process? We called it, oh, the bell rang? It's called convection. So as the more magma rises up, it pushes the plates outward. We had just talked about this in when we went over your lesson, or when we went over your assessment. But this is why. The convection of the mantle is what drives this whole process. I wish we had more time to talk about that, but you should know that that's true.